In this short talk, we want to revisit the derangement numbers. We saw in Chapter E on inclusion and exclusion that we can get a formula for the derangement numbers, dn, just using this inclusion-exclusion principle, but that formula is pretty complicated and involves a sum of terms that look like this, and we compute immediately that d1 is 0, d2 is 1, d3 is 2, d4 is 9, d5 is 44, etc., etc. Those can all be obtained with this formula. And when we look at this, we can see some patterns maybe. This 9 is 3 times the sum of 1 plus 2. This 44 is actually 4 times the sum of 2 and 9. This 265 is actually 5 times 53, which is the sum of 9 and 44. And then it continues like that. And that would suggest that there really is a recurrence relation going on here. We would guess that d sub n is just n minus 1, because, for example, here's d5 is 44, but it's 4 times the sum of the previous two terms. So d sub n is n minus 1 times the sum of the two previous derangement numbers, dn minus 1 and dn minus 2, and that pattern begins at d3. Now, how do we know that something like this is true? I want to run through with you a simple explanation for a combinatorial explanation for why, in fact, this really holds with derangement numbers. And of course, remember, d sub n counts the number of derangements of an n-letter string with n distinct letters. So we're going to think of the string 1, 2, 3, all the way up to n minus 1 and n. And in fact, I wrote it as a sequence, so let me instead rewrite it just as a string 1, 2, 3, 4, all the way up to n. So I have a string of n distinct letters. And we want to ask, how many derangements are there? Well, let's say I wanted to create a derangement. I'll put n spaces here, because a derangement will be a string with n terms, and some entry has to go in that first position. Because it's a derangement, that means no element stays in its original position. 1 cannot go into that original position, but any of the other letters in the string can go in that position. I'll call that letter x, and I'll say there are n minus 1 choices for what letter x, in this case what number x from 2 to n, that is. And then we're going to look at two cases on how to finish the string. Let's look here. Let's say this string, I'm going to write it really big. Here, this is an n-letter string. Here, n minus 1 letters, or spaces. This is where the x came from. In other words, that's the xth space. So let's say case 1 is that the number 1, moves into space x, so that there's a 1 here. That's certainly possible. Now the x and 1 have just interchanged places in our derangement. We have n minus 2 remaining spaces, and I claim if we want to fill those in to get a derangement of this original string, there are going to be d sub n minus 2 ways to finish. Why? Because these spaces can take any letters they want, except no number can stay in its own space. The filling in of these spaces just means find me a derangement of the string that contains all the numbers from 1 to n with the 1 and the x removed. If you derange that n minus 2 letter string and then put those elements in these spaces with the x and 1 interchanged here, you'll have a derangement of the entire string. What about case 2? And now for case 2, I'm going to erase the 1 here. Case 2 is that the 1 goes somewhere else other than in position x. Let's say the 1 goes here. Remember, this is position x there. Well, I claim now there are, well, let me actually write that in here. Case 2 is that the 1 moves somewhere else. I claim now that there are going to be dn minus 1 ways in which I could do this. Why? Because look at all of the n minus 1, there are n minus 1 positions here. And I want to know how many ways I can fill those n minus 1 positions with numbers from 1, 2, 3, up to x minus 1, and then we have x plus 1 up to n. This is the original string missing x. I want to know how many ways I can fill these positions with numbers from this string. And when I say how many ways I can fill these positions with numbers from this string, it has to be in a way that the entire string is a derangement of my original string, and now in case 2, I'm assuming that 1 does not go into position x. Well, the reason I claim there are d sub n minus ways to do that is if we look at this new string, I'm sorry, this is getting a bit messy here, instead of looking at this string, 1, 2, 3, up to x minus 1, skip x, and look at the remaining letters, put that 1 in the x position. In other words, look at 2, 3, 4, up to x minus 1. Now put in the 1 where the x used to be, and then continue from x plus 1 all the way to n. This is still an n minus 1 letter string. The number x has been removed. But I claim that any way I fill in these letters where the 1 doesn't go in the x position x, and the whole thing is a derangement, is just what I get when I take any derangement of this n minus 1 letter string and just fill it in. I've already filled in the 1 that's in the derangement of this string. The 1 can't go in position x, so that condition is satisfied. And all of the elements 2, 3, up to n can't go in their original positions. And now you see their original positions are kind of moved down once, so when I fill them in, they'll be in what were the original positions for those numbers in the original string. So any derangement of this string filled into these n minus 1 spaces will give me a derangement of my original string. So what have we done? We said first make a choice of what number x goes in position 1. So then by the product rule, I have n minus ways to do that times the number of ways I can finish the string. Well, how many ways can I finish the string? There are 2 cases. One case gives me dn minus 2 ways to finish. That was our case 1. And the other case gives me dn minus 1 ways to finish. And thus there are this many ways to create a derangement. And of course, that has to be dn, the total number of derangements of an n-letter string. And that explains this recursive formula for the derangement numbers. Now, there's another recursive formula for the derangement numbers, and that's this one. D sub n is n times d sub n minus 1 plus negative 1 to the nth power. You can check that here. 2, this number 2, that's d3. I'm sorry, let's say that again. D3, that's the number 2. I should have written that in, that this is D3. That 2 is 3 times 1, and then you subtract 1. D4 is 4 times 2, and then you add 1. D5 is 5 times 9, and then you subtract 1. D6 is 6 times 44, and then you have to add 1. And it continues on and on like that, and we can write that pattern by saying d sub n is n times dn minus 1 plus this minus 1 to the nth power. Now, the derivation of this recurrence can be done not in a combinatorial way, but just using algebra and the recurrence that we've already derived. In other words, once you know that this recurrence relation here holds, you can manipulate it algebraically and get this recurrence relation. That's the subject of problem F22, so I'm going to leave that to you guys to do at home.